We're happy to start the last two talks of the morning. And so, first talk is by Alexander Westphal, who's going to tell us about tensors in the landscape.
Thank you very much. Thank you for giving me the opportunity to be here in beautiful Cambridge and speak here, for being able to participate in the conference. So I'm going to talk about something that is to some extent still speculative. You can judge for yourself. Hopefully at the end I will try to make an attempt to explain that maybe we can start to estimate the distribution of tensor modes over at least regions of the landscape. Let's put it like this. So I have to qualify a little bit. So as you know, of course, we live now in this age of precision cosmology. We have some evidence for inflation in the past, and not yet maybe unique evidence, but in the sense of the observation of a near scale invariant power spectrum of density perturbations in the very early universe prior to decoupling. And based on that, basically, we should maybe be able to start to classify inflation models across the landscape of string theory. And there are basically like the simplest models of inflation. They have just two parameters. They have the spectral index of the power spectrum of density perturbations, and they have the amount of gravitational waves that they produce, measured by the fraction in power in tensor modes R. So, and the point is that this power of tensor modes is directly related to the scale of inflation. So if you ask about the distribution of the value R of the fraction of tensor modes, then you ask in the end, to some degree at least, about the distribution of the scale of inflation, modulo some loopholes that you already, that means you ask about, in a sense, for the distribution of an effective cosmological constant, which is large, which is not small like today, large compared to today, but still small compared to the string or Planck scale, because Kobe-normalized inflationary models have cosmological constants which are less than 10 to the minus 10 in Planck units. And then you have to ask about how they get populated, how they are distributed. Maybe this can be done, and I will try to give you some arguments why this is not maybe completely hopeless. So, for this purpose, I have to make some assumptions that for some regions of the landscape where we have some axes seem to be satisfied, and that I basically propose to take them basically satisfied because they are pretty general to hold across the whole landscape. And then you will see how far we can go from there, and at which point we have to specify to certain regions. So one of the assumptions is that basically that at the moment I want large tensor modes. Typically I need a large field excursion of the inflaton field. I need basically a trans-Planckian field displacement during inflation. And in order to do so, I have to control arbitrary numbers of dimension 6 and even higher dimension operators. And for that I need basically a symmetry. I cannot, it's basically a functional fine-tune. I cannot fine-tune away an infinite number of operators unless I have a symmetry that forbids them. And the symmetry that is so far basically has been shown that can do that. Maybe it's not the only candidate. Then this assumption would basically have to be modified. But so far we know that the shift symmetry can do that. It can basically protect the inflaton field from getting too worrisome radiative corrections and higher dimension operators that screw up the large field regime. So, but then you have to contrast this with the other fact that we seem to so far to have found in string theory compactifications to 4 dimensions, that the field range of every possible candidate that has a good shift symmetry, typically an axial field, is limited. And it's actually typically the fundamental domain is limited to less than the Planck distance. So if you were just to stop here, then you would say there is no large field inflation, right? So this comes basically from the fact that, as I already said, all those fields that have good shift symmetries, they tend to be have some periodicity, some fundamental domain that's limited. Typically they are axions, or they could be, for instance, also angles between branes. And when you canonically normalize them, you find that their field range is always suppressed by the size of the compact manifold, and that always gives you, in the end, that the field range is less than Planckian. So then, in addition, there will be the structure that was already in part discussed about the landscape of metastable vacuum, the zeta vacuum itself. So there are two basic facts that I will be using. One is that the mechanism that so far we know how to jump between different de Sitter vacua is tunneling, mainly Coleman-Lucia tunneling. This is the only way how we know how to get between the vacua, and I have to discuss how they get populated if I want to make any estimate. And then the basic structure so far that we seem to find is that at least in certain regions of the landscape there seem to be exponentially many vacua in a very high dimensional moduli space. And if you look at the de Sitter vacua among them, you take any de Sitter vacuum with a reasonably small cosmological constant and you go in moduli space to the next neighboring vacua, you typically find a large jump in vacuum energy. You don't get something like a tiny increasing washboard, but you get something that when you look up from your local vacuum, it goes very high. So all the neighboring, typical neighboring vacua have large CC compared to the scales of the CC, like 10 to the minus 10 or even smaller, that are therefore, the inflation describing our universe or even our late time cosmological constant, and that's something that you have to factor in. And then, of course, once you talk about that you have these many de Sitter vacua where part of the space-time can reside and inflate before even tunneling to other vacua, you have to talk about how to regulate the infinities coming from an internal phase of inflation that happens in these false vacua. This measure question is ambiguous. There are different measures that sometimes predict different results. There is no a priori candidate for a measure yet that is derived from the fundamental theory. So the point here is that if I will find that whatever comes out is dependent on the choice of measure, let's say by an exponential sensitivity, then I'm done. I can't do anything anymore because then we just don't know anything. The point will be that what we find is that unfortunately the purpose that I'm trying to analyze will not depend exponentially on the choice of measure. It's basically invariant. Regardless which measure I choose, I get the same qualitative answer, and that's what that's the only reason why I can proceed. So then the consequences of basically of the points 1 and 2 I made, that you basically you need a large field range if you want to produce tensor modes with single field models, and that those fields with a good shift symmetry have a restricted field range on the fundamental domain on their own. That basically, I mean, you have basically two possibilities to parametrically avoid that. There are some fields, there is for instance the overall volume, which can to some degree have an extended field range. So for instance the high fiber inflation models, they give you something like 4 or 5 Planck units and therefore basically scratch the boundary of detectable gravity waves. The point is that because they don't, the volume doesn't have a shift symmetry per se, a good shift symmetry, it doesn't get parametrical protection. So I'm asking here about basically parametrical statements. Therefore, I will have to use axion fields. And the axion fields, there are only two ways so far that we know how to give them a parametrical large field range. One is you have a large number of them and have them acting in unison. Then you get basically an increased field displacement, effective field displacement, and that may give rise to what was called inflation. So far, this doesn't have a full string embedding. There was made considerable progress by Thomas Grimm in the past, but this is not yet, I mean, it's open whether you can really embed this. And the other possibility, in principle, is, I mean, just from the definition of the word, you want to have a field that has a finite field range or is periodic even, and you want to give it a potential energy that doesn't see the periodicity. So you have to have some effect that generates monodromy in the potential energy. There are examples that have been found that use the energy of 5 branes, and in warped throats they will generate a linear potential for a 2-form axion, and that would provide, for instance, an example for a large field model that has like 10 or 11 Planck units for displacement for 60 e-folds, and may up to the bounds of stability give you even like a few Planck units more, like 20, 30 maybe, or something like that. But in general, here I don't care what the source of the monodromy is. I'm just saying that because all the fields have a limited field range, any large field model that deals with a single field will have to have some effect of monodromy. Otherwise, it doesn't give you the large field range. And these are just some examples that these sources for such monodromy exist. So this is basically what I said, that, I mean, based on these constraints on the field range, you need some form of monodromy if you want to do large field And that basically, and you need to use axions, because only those ones are the fields that have a sufficiently well protected shift symmetry, or have a chance to have such a shift symmetry. So basically you are forced to have some form of axion monodromy for a single field large field model in string theory, as far as we know. And using that constraint, you can parameterize the effective potential that you get from axion monodromy. There will be the monodromic, if you want, potential, the potential that isn't periodic in the axion field. Then there will be generically instanton corrections. They're basically, like, if you want, dependence on the field when it comes to the minima and maxima of that instanton potential is fixed. Otherwise, it cannot depend on the rest of the moduli. Otherwise, you would have broken the shift symmetry already with this term. But the magnitude of these instanton contributions, that will be a function of the rest of moduli space, right? I mean, in different points in moduli space, the magnitude of the instantons will be different, typically exponentially dependent on some of the moduli. And then you have the moduli potential for moduli stabilization, which is also there. So this is basically the kind of structure. When you combine this with the fact that, as I said, that when you go in moduli space away from a low CC or relatively low CC region of the potential, a valley or a minimum, that you basically go high up. The direct neighboring vacuum in moduli space tend to be of high CC then you find that, if you find some inflationary valley that supports, let's say, large field, or it could also be a small field region here, some inflection point, right? Then if you go away in moduli space, and this direction chi is summarily denotes all the other moduli. So you should think of this. This is a two-dimensional picture. This is deceiving. I mean, this should be like 100 field directions where you can jump away from this point. Then you typically jump up high. And the only structure that the neighboring high CC de Sitter vacuum will have is that it will have these instanton wiggles in the inflaton direction, because there is still the shift symmetry that gives you some structure in that direction. And this will be both true if you describe the eternal inflation happening in these high CC de Sitter progenitors, basically here. If you weight the volume here in some global measure, but it will also be true if you have local measures which basically are devoid of counting the three volume growth during an eternal inflation. They basically tell you that the progenitor of all the population will be some basically some de Sitter vacuum that is the longest lived, and that means that typically it will not directly tunnel into something else downward, but it will tunnel first upward and then from there downward. But still, these longest lived progenitors are high CC compared to anything that supports observable slow roll inflation or even the late time CC. You will always come from something very high down. That's the basic conclusion that you have here, right? And because of the shift symmetry and the breaking from the instanton effects, you see, I mean, that may be bigger than in your final inflationary valley, but you see that with respect to the scale of the CC in these progenitor vacua, these wiggles are typically small, and all these vacua are roughly equal, and it doesn't matter whether basically they will populate, they will come from here, and whether you tunnel from here to there or tunnel from here to there, you will find roughly the same, you will find the same initial conditions here. So this is basically, yeah, I mean, it's still a 2D representation. You basically, from the progenitors, which are high scale, you populate typically some very high scale vacuum, and from there you can very efficiently tunnel down. You also have this requirement that you have to come from high, not only because the typical neighborhood of any small CC vacuum are high CC vacua around, but also if you want to efficiently populate an exponentially large number of small CC de Sitter vacua to make this entropic argument by Weinberg to work, then you need to efficiently tunnel into them. You can only do this if you come from on high. If you come from something extremely small and tunnel upwards in most of the metastable other small CC vacua, you will never populate enough of them. It is too slow. So, and this you can basically, this asymmetry between tunneling up and tunneling down, you can see from the common de Lucia description of tunneling. You find that when you tunnel from some low, very low CC to a higher CC de Sitter, then and you tunnel into two different higher CC de Sitters, then tunneling into the higher one is suppressed basically exponentially in the CC of the smaller of the high-lying de Sitters. So you get punished for trying to tunnel up high. But if you tunnel downwards, then this is different. Then basically the overall tunneling rate is set by the overall tunneling rate is set by the CC of the high-lying de Sitter vacuum. But the difference in tunneling between from here to something of small cc here and something of a different but still small cc here. So let's say you have two low-lying de Sitter vacua with vacuum energies V minus and V minus prime. Both are small parametrically compared to the initial de Sitter vacuum cc, which is V plus. Then the tunneling rate will only basically depend on the change of the target space, of the target vacuum, cosmological constant, by a very suppressed effect. And at that moment, because we observable inflationary regions and late time CC, small CC de Sitter vacua, both have parametrically small CC compared to these initial progenitors, which are very high scale. Because that is the case, we do now see that and the tunneling rate does not depend on the tiny variations of the CC here. We can then basically say, because we have to end up here, I can then average the tunneling rate in coming down from the high CC vacua over all the, the varying barrier heights that are there in between. And effectively that means that if I compare two low-lying de Sitter vacua, V minus and V minus prime of vacuum energy, that the down tunneling rate by which they are fed from the high scale progenitors will be roughly the same, averaged over all the paths by which you come down from the high CC, on all the barriers that are in between. There will be no difference. Each different path will of course have a different tunneling rate because the barriers will vary from path to path. But because you have so many of these vacua where you come down from, you will in the end, you can average over the barriers. There will be, if you want, some average barrier height. And then you will have basically roughly equal population for all the small CC regions. So, if we are at this point, we have then now to ask what happens after you tunnel from some high CC vacuum into some slow roll inflationary region of parametrically smaller CC. What happens after tunneling to the scalar field that is supposed to drive inflation? The point is that if you come out and you have a so-called small field model that you could model with an inflection point, for instance, the generic small field models will be some kind of inflection or saddle point, and you exit at some point in the potential, then typically you overshoot very badly. So unless you would come out here, you would think they will never get populated. You will never hit them. Yeah, basically there would be no inflation started on the small field models after you come there by some tunneling event from some high CC vacuum. Because typically the high CC vacuum will not exit you here, it will exit you up the slope, and then you will be too fast here, you will not go into slow roll and you will overshoot. This was first basically noticed by Bruchstein and Steinhardt. This is the overshoot problem for both for moduli stabilization, sometimes quoted, and also for inflationary dynamics. But the point is that inside the bubble that the Common-Lucia instanton forms when tunneling down, you have a negatively curved open universe formed. There's negative curvature there. And initially the negative curvature dominates the evolution of the field completely. And if you, what I will show shortly is if you invoke the effects of negative curvature, you will find that even on such small field models, the negative curvature slows down the field evolution so much that in almost all these models you get tracked into the inflection point into slow roll. You do not overshoot. And on that note, you basically then know that the post-tunneling evolution that naively you would have thought would completely disfavor all the small field models actually puts them in the end, by virtue of the negative curvature inside the CDL bubble, it puts them on the same footing as the large field models. The initial condition problem there basically is largely relieved. I mean, large field models, they never have that problem. Even if you come in fast, they will slow down just because they have a large field range to basically slow from the friction of the cosmological constant generated here. Yeah. So basically you can, this is work that we have done in the past. You can basically model, try to first model such an inflection point potential by writing simple monomials for this steep part of the potential and then attaching something almost horizontal. Then you vary the initial height of the point where you get out, and you can then, for certain monomials, you can solve or at least bound the evolution from some math literature where the corresponding equations of motion have been studied as differential equations. And then you can basically show that you will always come in with such a small speed here that you do not overshoot. Yeah? And you can then also go on and combine several monomials and effectively, thank you, and effectively show that this is true for polynomials, and therefore in the end for general basically power series that give the potential close to the inflection point. So for instance, for the simplest case, when the steep part is just a linear potential, a steep linear slope, this was already studied in this paper by Freivogel, Kleban, Martinez, and Susskind in 2005, and there was some prior work where some general arguments were already noted that go in the same direction by Kachu and Dwali in 2003, where you see, and if you come down that linear slope and then you hit the inflection point, which is modeled by basically something almost horizontal, then you get some finite amount of overshoot, but that amount of overshoot depends on the displacement of the field from the inflection point at the point where it exits from tunneling. And if that displacement is small, then you will typically not get enough basically rolling that it will let you overshoot the inflection point. But again, I mean, a linear potential is, of course, a steep linear is a very crude approximation. So you can do this, for instance, for higher powers, for quadratic, cubic. Here I'm showing a result for a quartic potential that leads into the inflection point. And there you actually find that you come up with zero speed. And for every higher power too, regardless how high you start. When you start with curvature domination inside the bubble, you will always be tracked into the horizontal part with zero speed. So you will hit slow roll, regardless how narrow the inflection point is for these higher powers. Yeah, and then by combining this into polynomials, you can show that this is a generic property of most of the potentials leading into inflection points, as long as you have this curvature inside the CDL bubble there. Yeah. So if you combine this, that the post-tunneling evolution dominated by curvature removes the initial condition problem for most of the small field models and places them roughly on the same footing there with large field models, and then that the downward tunneling itself into every small CC region, both observationally viable slow roll inflationary regions, which have parametrically already small CC compared to the typical scales, and late time the small CC de Sitter vacuum as well, that this tunneling proceeds democratically. And then the post-tunneling evolution is democratic, so to speak. Then you find that effectively you have no strong bias, no exponential bias coming for the population of small or large field inflationary models coming from the dynamics that, at least the part of the dynamics we know that happens in this eternally inflating de Sitter landscape. So the prior from the dynamics, even if you account for the different measures, because they all predict you that you have to start on coming from a high-lying de Sitter vacuum. Otherwise, you cannot even efficiently populate enough vacua to make your entropic argument for the small present ACC to work. They combine such that there is no strong bias. And then the question of, do you expect large field or small field models to dominate, which would answer the question modulo some caveats also about whether you expect large tensor modes or not, is decided by counting. You have to actually now start counting. So this is something that I, at least personally, didn't expect. I would have thought that the measure completely kills me. Then I get some, e to the plus something big or e to the minus something big, for or against the same class, depending on the choice of measure, and then I'm dead with that question. But this, at least, it doesn't look like you get this strong bias, and then you can again play the same game as with the arguments about the present-day cosmological constant. You can argue the question about R maybe by counting. Counting we do not know how to do in full generality for the whole landscape, but we know it. We have some, as we heard today already, we have some evidence how to do this for certain regions of the landscape. Yeah. For the small field models, there are the random matrix methods that were reviewed in detail in the talks by Gary and Liam today, and there will be more talks on them, that basically give you an estimate on the fraction of metastables in the de Sitter vacuum that you have to take into account, and would also allow you to estimate what is the fraction of saddle points in the landscape that have one negative eigenvalue, so that the inflation could happen there, but the eigenvalue has to be so small that it's inflationary flat. Thank you. Yeah, you are probably able to estimate that question using the random matrix methods, I hope at least. And then if you have that, then you can at least, for let's say some region of the landscape, take the space of Calabi-Yau manifolds with supersymmetric stabilization of a large fraction of the moduli at the high mass scale. That example that Liam discussed on the last slide. Then for that case, you know that there's a large number of de Sitter vacua. There will be a large number of saddle points, and a certain fraction of them will be flat enough that this may be estimated from random matrix theory, and you will get basically some number for the number of vacua, and then some kind of correction factor that tells you how many saddle points you get for the fraction of stable de Sitter vacua. And these have to include, of course, I mean, they have to select it for that they are flat enough to support enough slow roll inflation on such an inflection point. And then you sum this over the number of Calabi-Yau manifolds, which we don't know, but you could estimate this by going to a sample of Calabi-Yau manifolds. For instance, in type 2b, you could take the Kreuzer-Skarke classification of toric manifolds, Calabi-Yaus that are constructed via GLSMs on toric ambient spaces. And then you could make a scan basically over those, right? And see what happens there. And then so these are basically like the overall number of this is how the overall number of metastable de Sitter vacua you would get, right? I mean, if you have the large number of complex suction moduli fixed at high mass scales by flux, and then a smaller number of Kähler moduli, you go to that region of Calabi-Yau space, then you can use these arguments that were shown earlier, and then you can estimate this. This would have to be found still, how many saddle points that are flat enough you get from a random matrix estimate. And for the large field models, the situation looks like you have to, of course, I mean, once I have an axion there, and the axion has its shift symmetry, it gets some source of monodromy to make its potential energy, then the point is that because of the shift symmetry protection, a large fraction of those existing, whatever flux generated de Sitter vacua in your, on a given Calabi-Yau will be basically consistent with that inflationary valley where you have the large field once it's there. So you can conservatively estimate an upper bound of the large field models by just counting the number of Calabi-Yaus that allow for the it is in the type 2b context here, that allow projecting in a two-form Raman-Tamont axion, just as an example. This should be you may be able to do by scanning over the GLSMs of such a you know, subclass of Calabi-Yaus. That's the Kreuzer-Skarke classification. And then you divide them, and you will basically, in the end, then get a result that depends on basically how many is a ratio of the fraction of how many flat-tuned saddle points, small field inflection points you get from a random matrix estimate versus how many what loss in Calabi-Yau numbers you have when you want to project in these axions. And if you can calculate those things, may be estimable, and then at least for that sub-corner, you may be able to get some estimate if those are parametrically different numbers, right? So this is basically the end of what I'm going to say, and the argument I'm trying to make is that the influence of dynamics from the landscape, of the tunneling dynamics, internal inflation on that question is less worrisome than I would have expected. And it may be possible to get partial answers for regions to this question by really doing counting, by doing statistics. And if this can be done successfully, I mean, it would be nice to know, right? I mean, you may have correlations that for a certain region that supports low energy supersymmetry, you get one or the other outcome of this counting question, of this ratio that I showed. And it would be maybe nice to know this, given the coming experimental data. Thank you very much.
Time for questions? Scott?
The initial value of the kinetic term of the scalar field typically depends on the thickness of the bubble wall and the location you tunnel to, right?
The initial, yes, the initial value will vary depending on where you come out. Yeah.
So it's the result that you get the zero value. That's a special choice where you're looking at the thin wall approximation, or? I would have thought generically you would tunnel to arbitrary locations and you get arbitrarily initial kinetic terms. I guess that's the part I don't understand.
You mean arbitrary initial values of the field after tunneling, basically?
Yes, yes.
Yes. Yeah, but this but this was the point. I mean, we basically showed that regardless of the initial value of the field, in the vast majority of cases, the field gets slowed down by the evolution, by the curvature inside the bubble, so much that you are tracking into this.
No, I don't mean the initial. Sorry, I don't mean the initial value of the field. I mean the initial value of phi dot.
Well, that is for the Coleman de Lucia. I think the fact that the initial condition is set to 0, that phi dot is 0, I think that doesn't rely on the thin wall approximation, as far as I know. But even if we actually looked at this, these solutions, if you give them finite speed, say on a quartic potential, the example I showed. If you give it some phi dot, it still tracks into 0 speed on the
But
inflection
are
point.
you bounding it by like m Planck squared or something, or?
Uh,
I'm asking because
Yeah.
in general the small field had two problems, right? It was one, the initial value of the field, but also the kinetic energy before you enter the inflationary.
No, but the evolution equation you get under the dominance of initial dominance of curvature for, let's say, the quartic potential that leads you into this horizontal region of the inflection point. For arbitrary phi dot, it can be bigger than m Planck. I don't care whether it's bigger than 1 in Planck units or less. It will always track into 0 speed. This is the property of the solution you get there. And this is true for everything, but just quartic, quintic, I mean, for every higher power you have there.
I have two questions. One is that one of the organizers of the conference, who's not me, wrote 2 articles about the difficulty to get a large-scale inflation, and in particular this action monodromy and so on.
Yes.
What is your answer to that?
So, yeah, diplomacy is not my strong suit.
Not mine.
How do I answer to this? Let's put it like this. I mean, the question is how long do you want the answer? I mean, I have already used up my time.
I'm missing for lunch. So
Yeah. I mean, for a short answer, I would say I have my doubts about the results presented there. I'm not saying that what was the calculation, the Manu calculation, calculating the 5-brane interaction potential, that is supposed to give a strong, or it was argued to give a strong back reaction effect on the whole geometry. It may be that such an effect can happen, but there are ways to actually, if you want, warp this whole effect down, and then it doesn't affect the UV endpoints of the compactification. And then on the other hand, the calculation was done in flat space, and we know how difficult it is even to derive a classical warped effective field theory. We do not know how to do this calculation in warped space. And I have difficulty in actually just directly using the flat space result and taking it over to the warp case and saying it presents the same difficulty there. The other thing is that the physical reason behind, or the physical argument that was made for this one-loop calculation was that because the charge of the 5-brane doesn't get warped down, charges don't warp. I agree with that. Like you throw an electron in a black hole, that argument was given. You'd see the charge of the black hole after that if you put a Gaussian surface around it, right? To make the Gauss law integral. The charges don't warp. But then, as far as I understand the argument, this was argued to be that because charges don't warp, you expect in the end a strong metric back reaction. But the metric perturbations are sourced by energy momentum. This is how I understand the Einstein equations. And energy momentum itself redshifts, even if the charge of the object doesn't redshift. Though I'm not sure whether I would expect, just from the fact that there's a force attached to the charge, that I will necessarily get a strong back reaction on the geometry per se. I would have to do the full warp calculation to see that, and I don't know how to do it.
I think the burden is on you. The burden is on you. You are the one who has to show that.
I know. The other thing is, as I said, there is a way, even if the effect is there. If you set up, I mean, yeah, okay. Well, let me draw some diagram. Please excuse me if it looks obscene. Is this a normal? Can I use this here, or is this? Yeah. It looks like one for a whiteboard. That's why I wasn't aware. So in the original setup for axion monodromy, what you had basically, maybe I have to draw it bigger because otherwise.
Why don't you do this side? Maybe?
Yeah, it's
This side? You want to send me? Can you lift this here? This is
no.
You got 1 minute.
No, here.
You have some Calabi-Yau which has a UV bulk. You imagine you engender a geometry which has 2 throats, which basically directly mount into the bulk. You enforce something like a geometry where you have two cycles that are connected by some, if you want, we'll call this a 3-chain, I guess, like a banana. The connection so that they are related in homology. Then you put 5 branes here, a 5 and an anti-5 brane to satisfy the 5 brane, and also a potential 3-brane charge tadpole. And then you put a C2 axion on this here and minus C2 on here. You crack it up, and then, as I said, this is supposed to give you a linear potential. Now the point is, so to speak, there is 3-brane charge that is built up here, and that back direction we accounted for in quite a lot of detail. And basically this gives you bounds in the field range. You cannot go arbitrarily far, but you can go from that point, from the three-range charge argument, far enough to get you like several tens of Planck units. Now the calculation that was done in the paper you were referring to is basically that the 5-brane charge also gives a force that's threaded along these things, and the calculation done in flat space in this work suggests that there is an effect coming from the UV region, which is so strong in backreacting on the geometry that it screw up the whole thing basically. So let's assume this thing is there, and it is as bad as it is claimed in this work. Then we basically already, for having better parametric control on the backreaction of the 3-brane charge, we had basically a follow-up later, where we basically assumed that you don't set up this thing like this, but you first make a single parent throat coming from the UV that's stabilized by sufficient amounts of 3-brane charge basically down here, and then from there you branch off in your 2 throats where the 5 branes sit down here. Yeah? So and then the banana would reach like this. The point is now the UV scale of the effect would be the IR scale of that throat. It would never do anything here. And then by arranging,
is it too baroque to realize that?
it is baroque. I'm not saying that these models are beautiful in the sense that they are elegant.
No, but it's possible.
But there's still an entropy problem, right? That's the second point of the criticism. That's more in quantum gravity.
That argument I also basically, as far as I understand the argument, it is a parametric argument, and it is the weakest when you look for single field.
Yes, I mean that applies more to things like entropy.
Yeah, exactly. And there I would say the argument probably certainly would imply, the entropy argument from the other work would certainly imply that you cannot go to arbitrarily large field range. You probably would never giving this argument, get large field eternal slow roll inflation by quantum diffusion at 500 Planck units out on the potential. But that I already get from the 3-brane charge bound. It will never allow me to go that far. I would boom bust the compactification before that. So that may well be true. But as I said, since we are interested in getting 60 e-folds at the first point, this is it does not run yet into that bound because there's a parametric bound. That's how I understand that. But as I said, for the other argument, even if this calculation gives this result that was claimed in the warp case, and it has this bad effect, then there is a setup where this can be easily warped down and brought under control. Yeah, easily in the sense that to the effect that warping eases up things. I mean, in the sense that you get a reduction. How to set up such a geometry in a compact global model is difficult. I agree. I mean, this has not been done so far, and this is something that actually would be really nice. Actually, maybe these works that have been done on these F-theory compactifications that give these del petzels that are exchanged by orientifolds. This would be exactly the type of structure where the dual 2-cycle would be of that kind of type. So maybe actually this could be done. One could look for this and then scan for H11 minus equal 2. That's what we need basically, models. Because you need 2 of these 2 cycles that each carry an axion connected in homology. By scanning over these kind of models, maybe this is possible.
Okay, let's thank the speaker again.